Today I would discuss Cauchy-Schwarz inequality, its proof with method 1. It states that if a1, a2 up to an and b1, b2 up to bn are real numbers, then we need to prove summation I from 1 to n ai bi square less than or equal to summation I from 1 to n ai square into summation I from 1 to n bi square, or we can say that mod of summation I from 1 to n ai bi less than or equal to root of summation I from 1 to n ai square into root of summation I from 1 to n bi square. This is the statement of Cauchy-Schwarz inequality. Now let us start the proof. Since we know that for all non-negative real numbers a and b, the geometric mean of ab, which is root of ab, it is less than or equal to the arithmetic mean of ab, which is a plus b by 2. This holds for all non-negative real numbers if we have x1, x2 to xn and y1, y2 to yn. If they are real numbers, if these elements are real numbers, then for x1, y1, root of x1, y1 less than or equal to x1 plus y1 over 2, and so for x2, y2 we have root of x2, y2 less than or equal to x2 plus y2 over 2, and so on. For xn and yn we have root of xn, yn less than or equal to xn plus yn over 2. So these are n number of inequalities. When we add the left hand sides and right hand sides of these inequalities, we get the sum as follows: I from 1 to n summation I from 1 to n root of x I y I less than or equal to summation I from 1 to n x I plus y I over 2. This is numbered as 1. Now we suppose that a is equal to root of summation I from 1 to n ai square and b is equal to root of summation I from 1 to n bi square. We suppose the values of a and b are as root of summation ai square and root of summation bi square respectively. Since one is true for all non-negative real numbers, so uh, we take some non-negative real number xi, which can be written as xi is equal to bai square over a, and we choose alternatively yi equals to a bi square over b. When we put all these values of xi and yi in our equation 1, we get summation I from 1 to n b ai square over a into a bi square over b, summation I from 1 to n b ai square over a plus a bi square over b divided by 2. When we simplify the left hand side, we get summation I from 1 to n, that's equal to b is cancelled here and a is cancelled here, when we get a I b I whole square, it's under root. Less than or equal to 1 by 2 is constant, so we can take out 1 by 2 because it is independent of I. So this constant is taken out and we get inside here summation I from 1 to m b ai square over a plus a bi square over b. Since we know that root of since root of x square is equal to mod of x, so we get summation I from 1 to n mod of ai bi less than or equal to 1 by 2. The summation is separated among these two terms, this one and this one. So we have b ai square over a plus summation I from 1 to n a bi square over b. We get summation I from 1 to n ai bi less than or equal to 1 by 2. Here b over a in the first term is independent of I, so we can take out b over a, and inside we have I from summation I from 1 to n a I square plus a by b. A by b is independent of I, it is taken out and we get summation I from 1 to n bi square. Since our a and b are root of summation ai square and root of summation bi square respectively, so in this inequality We have summation I from 1 to n ai bi less than or equal to 1 by 2 b over a. This is equal to a square, and this is equal to b square. A square and this is equal to b square. We just put the value of a and b, because a is equal to root of summation ai square, and b is equal to root of summation bi square, and hence we get um, b over a into a square plus a over b into b square. When we simplify, we get 1 by 2 b a plus ab, that's equal to 1 by 2 into 2 a b, and this is equal to summation I from 1 to n um, mod of ai bi less than or equal to, here in this term 2 is cancelled, so we get a into b. This is named as 2. In the system of real numbers, we know that for all x y belongs to the set of real numbers, mod of x plus y is less than or equal to mod of x plus mod of y. So we can have, by using this inequality, I from 1 to n a I bi, its mod, this should be less than or equal to summation I from 1 to n mod of ai bi. This is due to the above inequality, mod of x plus y less than or equal to mod of x plus mod of y. That's very simple, I think. You can easily understand. So, and this expression, summation mod of ai bi, what is that? By equation number 2, summation mod of ai bi is less than or equal to ab here. So it means that this is further less than or equal to ab. This implies that mod of summation ai bi I from 1 to n less than or equal to ab. And what is ab? Our ab is a root of summation I from 1 to n ai square, and b is a root of summation I from 1 to n bi square, which is our required Cauchy-Schwarz inequality by using first method, hence proved.